Okay, before we start, let me tell you about the report. So I'm gonna post the assignment on LMS as soon as we finish our lecture today. And in the assignment, I will post a file, a zip file, containing the template that you can find in the Notion, the same template file, and also some instruction README file and some folder if necessary. And you have to read the instruction carefully, but I'll briefly tell you how you should write your report. It's not the content, it's not about the content, it's about the format. So in the zip file, when you open this MD file, you can open it in any place, any text editing program, like a memo pad, whatever you want. But you shouldn't copy paste this content into Microsoft Word or Hangul program. It's not the content that you have to write. It's this file that you have to write your report. Just write on this file, okay? Don't copy paste this to another program, okay? Just write on this file. This is the text file. It's same as just the .txt, just made it into different extension MD, okay? But if you write in here, it's not advised because you don't see how it's going to be encoded. So I advise you to open up VS Code, and you can put your MD file or entire folder in any place that you would like. Let's see here. Let's say I open up the template file here. And if you click on the icon on the right here, you can see how your file is encoded into nice format, readable format. So again, this is just a preview, and I don't want you to print out this preview in any other format. I just want you to submit this MD file with the content you typed. So when you type the content, you can write anything here. So it will appear in the preview if you want to see it. So write the content here. And there are three things that I want to emphasize. First, if you need to, or you should in some places, if you write the formula, math formula, don't paste an image of a formula. You can write the function formula with the $sign around it. So if you put y equals f of x as your formula, if you want to put this way, then you can do inline formula using this function. So it's not a function. So this is a type any text here, but I'm showing you that you can put your inline formula on your sentence using this $symbol. And if you want the separate line, giving you a formula in a separate line, then you can use double $symbol here, so you can see that there is a inline, not inline, it's a separate line formula across the entire span of this line. So you get the formula function. And also, if you need to input some special characters like theta, there is a command that prints that symbol. So you have to search for LaTeX symbol. So here, for example, if you want to put the theta symbol here, there is a command \theta that gives you the theta in print. So you have to use the appropriate symbol anytime you want to use it. And also for formatting of the objects such as matrix, there is a way you can make a matrix. For example, if you want to write the matrix 1, 2, 3, 4, then the LaTeX command for matrix is this one. there are other types of matrix you can use. Instead of B matrix, you can use P matrix. So if you put the command, LaTeX command, and then open up the preview and then see whether your command prints the formula nicely and correctly. And that's the one thing for a formula. So don't paste the image here. Now the second thing is about image again. So this is the text file. You cannot post the image here. It's simply a text string. So the only way you can, if you want to, attach your image is making a command posting an image. So here, my report file is on the folder that contains a subfolder called image, and there is inside the image I have this 0-1 PNG. So if you want to post an image, then this is basically how the command that you should post your image. Put your image file folder and then name of your image file, then it appears here. So there is a way you can adjust your size of the image. Let's say if you want width to be 100, let's see, how is it? I think width. I think it's getting smaller. I think maybe center. It doesn't work anyway. So there's a way you can decrease the size of them. So that's how you should post your image. So that means when you submit your work, you have to put your MD file and the image file attached together, so that when I open your MD file, I can see the image when I preview it. Okay, so that's how you post your image. And also, third thing is that if you need to write your code, don't put the image of your code. So I see that many places in your Notion presentation, some people just post the image of your code. Don't do that. So there is a way you can post your code using code snippet. So put the a single quote sign ending with the 3 quote sign, and there is a indication that what kind of language are you're trying to put in between. So you can post your code snippet like this. So this is where you should use your code here, and don't put the image of your code. And this is basic things that I want to emphasize. I will post the detailed instruction again, so please read carefully. If I see anyone submit PDF file, Word file, Hangul file as your report, I'm not gonna accept that, okay? So simply put this MD file with the image, attach the image inside of the folder, and then so I'll put also instruction how you submit your work. You have to zip your entire work into single file and then submit it as a report. So any questions about this format? Any questions? So everyone clear? Everyone clear what to do on your report? Okay. By the way, so if you want to add more subtitle or sections, then you can do so. You can actually change the title or subtitles that I put it as a template. But by the way, don't forget to put, let's say, all the necessary information, for example, like project number, names, or student ID. Other than that, this is just a template, so you can change your the title or subtitles or subsections. If you want to add or modify, you can do so. Okay, so that's that. And so we finished our last lecture explaining about the conformal mapping. And I posted video on the Notion. It's not the same lecture I gave yesterday, last time, because I forgot to record the lecture last time. So I made a video, another video again. So today I'm going to finish the presenting project 5, and I think I couldn't move on to project 6. I couldn't on the I didn't have time to explain the project 6 in the morning class. So if I finish early, then I'll finish the class early. Okay, so let's think about project again. So visualize. The project is to visualize the heat map on the disk. So what is the disk? So disk is simply the set of all points inside the unit circle. Okay. But so what is the heat map? So heat map is actually the function of temperature at every point. So I'm assuming that inside of it, outside of the disk is insulated. Inside there is a heat can flow inside, and I'm assuming that the boundary temperature is fixed here, but it's not fixed at the same point, but same temperature, because if I have the same temperature all around the circle boundary, then the inside is always the same temperature, right? So I have different temperatures, C1, C2, C3, C4, and I want to know at any point inside of circle what's the temperature. So I want to find the heat map D on R, which satisfies the heat equation. And I want to say, H to satisfy this the boundary condition. So this is our goal. Okay? So this is our goal. Now, finding such map H is hard when you have dealing with the disk, and because the boundary is circular and it's hard to formulate the parameter. So we are going to find this map through opera plane. So I'm going to first transform that disk into the opera plane H, where opera plane is simply a set of all points in two-dimensional plane where y coordinate is positive. And on the opera plane, I'm going to find a map H to R where it satisfies all the same condition that our goal requires. So H, the small h, is harmonic map, so satisfying this partial differential equation, and with boundary condition compatible with the boundary condition on the disk. So what I mean by compatible is I don't want random boundary condition on H because it must match with the boundary condition on disk. So when I transform the disk into the opera plane, then each of the boundary is also transformed to the boundary of this upper plane. The boundary of upper plane is the real line, the bottom line here. So, so since we split it into 4 pieces of boundary, then on upper plane that also becomes the 4 pieces. So here we have 1, 2, 3, and 4. So actually it depends on whether your point that splits the boundary is the point corresponds to the infinite point on the upper plane, but let's make it this way so that you can just simply think about the boundary. So say we have C1, C2, C3, C4. So I want each of the pieces of boundary on the upper plane to match exactly the same pieces in the upper on the disk here. And also we want this condition because we want the heat function. So D here. So once we have, let's say this is our T, okay. So once we have this map T and H, then what we're going to do is take a composition of T and H so that this composition becomes our H that we want to find as a goal. So in the last time, we actually did the opposite. We found the map from upper plane to the disk, which is conformal. Okay? But we're going to find it opposite. So D to H. And then we're going to find small h. And then we're going to combine it together to see what's the heat map. So first, let's start from the the conformal map from disk to H. So I'm not going to go to the definition of conformal map again, but think about how we did it. So we thought D and H as a subset of complex plane, the set of all complex number. So we could translate this function into the function of complex number. So if I take the point in the disk as a complex number z, writing in x plus yi, and let's say a point in h square is the complex number w, and I want to find out the real part and imaginary part of w as an image of z. So if w is equals to tz here, it's going to be some ux comma y plus vx comma yi. So u is the imaginary part of w and v is the u is the real part of w and v is the imaginary part of w. They are both function of x and y, where x and y are the real and imaginary part of z. So I want to find the formula of u and v. So what's the requirement here? I want, so here we are going opposite, these 4 points on the disk, I minus 1, 1, minus I. Now, remember that we are looking at disk as a subset of complex number. We're not talking about 1, 0, 0, 1. Instead, we're using the complex number. I want these 4 numbers to map to these numbers. So minus 1, 0, 1, and infinity. So infinity is not a number, but in the conformal mapping like this, you will actually end up getting infinity as a number or point that matches to one of the point on the boundary. So here's the mapping. So minus 1 I maps to 0, 1 goes to minus 1, 1 goes to 1, and I goes to infinity, and actually 0 is going to I. So let me write it out here. Minus 1, minus I, 1, I, 0 are mapped to minus 1, 0, 1, infinity, and I. So through the function t. So I'm going to find the t as the form of following. So it's something like this. So tz is always in form of rational or fraction of two complex number. Each numerator and denominator are linear function of z, and the coefficients are also complex number, alpha, beta, gamma, delta. It's hard to find by setting up the equation, so I'm going to show you how it is. So it's actually done by last time. So I want to show you again. So let's look at the number 0 on the disk. 0 goes to, sorry, let's think about 0 here. So let's think about I on the disk. It maps to 0. So if minus I goes to 0. If minus I is mapped to 0, then the equation like this, you must have 0 on in the numerator, because the result must be 0 only when the numerator is 0. So you must have something like z plus I on your numerator. So I don't know about the denominator, but at least I need to have this, and also some coefficients going on here. So that's one thing I can say about the t. And let's say I want to send 0 to I. Okay, so I want to send 0 to I. That means, okay, so if I plug in 0 in here, right here, then I should get I at the end. So here is set here, and what I don't know is the coefficient of set and the constant. So here I need to know what is z multiplied to and the number that it added to. But if I plug in 0 in these places, two places, then I don't care what this is, and all I care is what this is. So therefore, on the top, what I have is this thing and this thing, and let's see. Well, I think it's I should start from the guessing here. So I'll try that. Let's see. I'll try that this one is 1. Okay, I'll try with this 1. Okay, and let's try out other points. How about -1 here? Okay, so I want to get -1 when I plug in -1 on z. Okay, so that means -1 plus I multiplied something over something -1 plus 1 equals to -1. So, okay, so what it should be? What should it be here? So let's guess. So it's not a guess and check, but the way of finding alpha, beta, gamma, delta can be done by guessing. So once we find alpha, beta, gamma, delta, there is only one possibility. That's why. So if I want to get -1, then the possible way of having this is having 1 here and I here, right? So then numerator is I minus 1, and denominator is minus I plus 1, which is exactly minus multiple of the numerator. So I can guess that I have 1 here, so I can erase this, and here I have minus I and 1 here. No, so just I. So since I plug in -1, so minus I is getting by taking I times -1. Okay. So let's check whether it matches to our previous tests. So if I plug in 0, I get I. That's right. So I get I. When I plug in -1 here, t of minus I, sorry, is minus I plus I times minus I plus 1. So I get 0 over 2, so I get 0. So that's right. And I had checked already minus 1, so that's fine. So let's check the other 2 points. So how about I plug in 1? So if I plug in 1 in here, then I get T1 equals to 1 plus I, which is 1. So that's fine. So I think now everything is okay. Because the last part, it's tricky, but um, it's tricky because I don't want to introduce this kind of computation because it doesn't really help you understanding the number. But so when I plug in I here, so Pi is equals to I times I plus 1, I plus I. So it's a 2I in numerator, but in the denominator, it's I squared plus 1, which is minus 1 plus 1. So you have a 0 in denominator. So it's in the text of, so you will learn how to deal with this kind of thing in engineering math too. So in the complex space, you sometimes consider this minus 0 on denominator as something that's equivalent to infinity, considering the infinity is also a number. So we can say that minus 1 is mapped to infinity in this case. So everything matches well. So what is the final form? This is our form of t. This is not what we want. We want the t in this form so that we can translate it into 2 to 2 function. So let's rewrite this as a real part plus the imaginary part. So it's I z plus 1. Let's just take the conjugate of this and I z bar plus 1. Or maybe I can just rewrite this into I x plus yi plus 1 and x plus yi plus I. And then let's make it real and complex imaginary part. So minus I plus 1 plus xi, that's a denominator, and x plus y plus 1i. Okay? And then, in order to find the real and imaginary part, you multiply the conjugate of the denominator up and bottom. So minus I plus 1 minus xi. And then on the top, you get x plus y plus 1i multiplied to minus y plus 1 minus xi. So what you get is 1 minus y plus x squared. And then on top, the real part is x minus y plus 1 plus x y plus 1. And the imaginary part is x minus x squared and y plus 1 minus y plus 1 I. So let me summarize here. So at the end, what you get is x squared plus y minus 1 square. Is it right? Yes. It's okay. Minus 1 square y1. Yeah, so okay. Yeah, so that's right. So and then 2x on numerator. And then you have x squared plus y minus 1 square. And then it's 1 minus x squared minus y squared I. So now we found u and v for my t. So t that sends point in disk to upper plane is given by 2x x squared plus y minus 1 squared, 1 minus x squared, y squared, and x squared plus y minus 1 squared. And that's our t. So one part is done. So what's the next part? We need to find the map from opera plane, this H, opera plane to the R, satisfying the heat equation, this partial differential equation. So now we need to talk about the theorem. So here's the theorem that so we're gonna just introduce the theorem, and then the deep theory will be left to the question if you want to. So let's say we have function xy goes to uv. If this function satisfies following equations, then uxy and vxy, they both are two variable function, real valued two variable function, are harmonic function. So harmonic function. So what does it mean by harmonic? It's the same thing as the heat equation. So harmonic means that it satisfies this equation. And same thing for V. So what is the equation that has to satisfy? There are two. One is ux equals to vy, and the other is uy equals to minus vx. So it's a necessary condition, not sufficient condition. So I'm not saying that any harmonic function is satisfying these equations. Okay. But it gives you a way you can find how you can find the harmonic function. All you need is find the two variable function having this. And if you know the complex function theory about complex function is comparatively easy, what you need is finding a function that is purely in terms of the complex number z. So I'll give you the example. So if you take, let's say here, hxy equals to, let's see, theta of xy, this is harmonic. So which means that if you plug that into the differential equation, partial differential equation like this one, is satisfied. So what is theta xy? Theta is the angle, the polar coordinate, one of the polar coordinate of x and y. So when you have x and y right here, and this is r, and this is theta. So here we are assuming that x and y lies in the upper plane. So we're not interested in the angle bigger than theta. We only think about angle between 0 and pi. So we can rewrite this theta as the inverse cosine, because inverse cosine gives you the angle between 0 and pi. The cosine inverse, if you want to find the cosine inverse of x and comma y, it's x squared plus y squared x, right? So it's a function in terms of x and y. Do you know how to take the inverse cosine, derivative of inverse cosine? What's the derivative of inverse cosine? So ddt of inverse cosine is when you take the cosine t as y, it's the inverse reciprocal of ddy of cosine y, right? So what is the cosine y, derivative of cosine y? It's a minus sine y. So what is it? Sine can be written as 1 over square root of 1 minus cosine squared y. So therefore it's minus 1 divided by 1 minus. What's the cosine y? It's t, because that's how we define the cosine inverse. So it's a t squared. So that's your cosine inverse, a derivative of cosine inverse. So when you try to get the partial derivative of h, del that x h, you can use the inverse cosine derivative. So first, it's a minus 1 square root 1 minus of everything inside here, cosine inverse. So we have x square root x squared plus y squared. And then you take the partial derivative of inside, which is x squared plus y squared and x. Okay, so you can keep doing the computation until you get purely in terms of x and y without any operation, partial operator. Then, in order to check whether h is a harmonic function, you have to take the partial derivative again to get the first summand of your equation. Then you get to the second summand. So it's getting complicated. However, I'll show you how to check whether that function is harmonic or not in an easier way. So what we are doing here is trying to apply this operator, the operator involving the second order partial derivative, onto a function. So I want to translate this partial operator in terms of r and theta. So let's say I have, let's see, okay, so I'll use it this way. So r theta transformed into r cosine theta, r sine theta. So this is a coordinate change, okay? So what is df? It's cosine theta, sine theta, sorry, so it's cosine theta minus r sine theta. So I'm doing just partial derivative of r cosine theta, first with r and second by theta, and then take the partial derivative of r sine theta and sine theta and r cosine theta. Okay. So again, I'm trying to show you how to convince yourself that why this h is harmonic, because just applying this partial operator is so complicated. So I'm going to write this partial operator in r and theta operator. So this differential gives me that information about the partial operator. It says if I have del x and del y, and so since it's x and y, I can rewrite this as cosine theta minus sine theta, r cosine theta. Okay, actually it's opposite, right? So del x is same as del u del x del u, and del v del x del v. So that's the chain rule. And also another equation is del u del y del u, and del v del y del v. So this is a chain rule that I introduced last time. And the way you can memorize this chain rule is that everything u or v are a function of x and y. So you want to count all the u and v in the change of x and y. And also you can consider that u here are cancelled out to get just dx here, and v here it cancelled out to get just x here. So that's why you get del x, and same for del y. And okay, using this, let's rewrite our equations. So del x is same as, what's ux right here? It's cosine theta del u, and what's vx right here? It's sine theta del v, and here what's del y? It's right here, minus r sine theta del u, and here what's del vy? So it's r cosine theta del v. Okay. So what we are doing here is trying to get this one. So it's same thing as taking del x on del x, but del x can be written as the sum of del u and del v. So we can just put the cosine theta del u, and I forgot r here, right? Oh no, just sine. Okay, so sine theta del v. And then same thing in here, del y on minus r sine theta del u and r cosine theta del v. Now, how do we actually do the partial derivatives on partial derivative? So you do it by symbolically. So del x is again this partial operator, partial derivative operator. So here, so I'm going to write a little bit abbreviated form because it's hard to write everything down here. So this is del x sine theta del v, and operating on the same thing, del x. Okay, so let's compute the second part later. So let's concentrate on the first part. So what we're doing here is, sorry, so not u. I'm gonna keep using u. So it's r and zeta, sorry. So it's r zeta. Let's change it to r zeta. R and zeta, sorry. So it's, sorry. So this is not part. So del x, there are, there's theta, there are, there's okay, so now I should change this to somewhat it's getting complicated than I thought. So anyway, okay, so let's change it this again, and then I'll explain more. So we have r theta here, and then okay, so forget about what I just said here. So so here these are x r x theta, y r y theta, but what we want is actually the opposite. We want these, right? Instead of x derivative by r, we want r derivative by x. So how can we get this? So actually we get this by taking an inverse of function f. So let me move this a little bit further down here. So if you have f mapping r theta to xy, let's say you get f inverse mapping xy to r theta. I want to find out the derivative of this inverse function. Then each coordinate of this inverse function matrix is rx and ry and theta x, theta y, which we really want. But how do we get this inverse? By chain rule, because we know that f inverse times the function original function can be computed by same thing as the derivative of the composite of these two functions. But if you take the composite of inverse and original function, it's identity function, and its derivative is identity matrix. So we know that the derivative of inverse is inverse matrix of the original matrix, original differential here. So this is actually equal to inverse of this. So it's a cosine theta minus r sine theta and sine theta r cosine theta inverse. So I didn't mention how you take the inverse from matrix, but it's a matrix that if you multiply to the original matrix, that gives you the identity matrix. I'll just show it here. So it's a 1 over to the determinant, which is r in this case. I'll talk about determinant later. And you have to switch the diagonal entries here, r cosine theta and cosine theta, and you put the negative sign on the off diagonal, so it becomes r sine theta and sine theta, minus sine theta. Okay, so that's your inverse, and that is your rx and xx. So let me put that in here. What's rx? It's cosine theta, because r cosine theta divided by r is cosine, and there are. And what is theta over x? So theta over x is this one. So it's a minus sine theta divided by r, there's theta. And same thing with r y is this one, so it's a sine theta, there, y, r. And here we get cosine theta over r, there, theta. Okay, so now I have a different formation here. So we have erased this one. Actually, I have to erase this part too. Erase this part. So what happens here is now I have del x, same as cosine theta del r minus sine theta r del theta, acting on the same operator again, c theta del r minus sine theta over r del theta. And there's another part, del y squared. But let's skip this part, and let's show you how you can compute this part. So it's the same thing that you applied operator. So you want to operate this operator onto here. Okay, so c theta, there are operating on c theta, there are is same thing as c theta. So this is just a constant, so we can leave out. And when you take the operator, this is a differential operator, a partial differential operator, on to a multiple of two functions, so you can consider this as also function. You take the product rule. So first, you take the partial operator del r to c theta, and then keep the next product, and then plus you take the delta r, apply to delta r again. But what happens when you take the two differential operator acted together? It's a double partial derivative. So that's the first part. Okay, so yeah, so that's the first part. Okay, so that's the first part. Let me keep this part. So there are other three more summand here, but let me skip this part. So what's this? So here we get partial derivative of c theta, which is purely the function of theta only, and taking the partial derivative with r. That means it's 0, right? So we get 0 here. So we get no here. We have c squared theta, and there are square. So you can do it to get all the partial derivatives or operators. And what you end up getting here is, let me go to our slide because it's getting long. So I think I have one in here. So here, right here, yes. So once you can do all this computation, you get this. Okay. This is the same operator that you have for the definition of harmonic map. So if your function is defined in terms of r and theta, you can apply the right-hand side operator onto it so that check whether it becomes 0. So what does it say? Del r square plus 1 over r del r plus del r square del theta square. So let me copy here. Del r square plus del r, I think square. Yes, and plus r squared del theta square. Okay, so why are we doing this? Because we are trying to check our function h x y. If I represent this r in terms of r and theta, it's simply just theta. Okay, simple theta function is harmonic map. So if I try to apply this operator on h, it's same thing as applying this operator on h, which is just theta, and look what you got. So when you take the partial derivative of h theta with r, you always get 0. So there's no effect of having this operator on. And also, if you take the second operator, a second partial differential operator on h, theta with theta, so theta is here, the linear map, linear function. So every time you get the second partial differential, it's zero. So you'll always get zero. So theta map is always just harmonic map if you consider that as a function of x and y. Now, why do we need this? Because we need a harmonic map. And also, we need a function that I can control the value at the boundary. So how can I control the value at the boundary? First, so let's think about the value of h first. So h, let's see, x and y is simply just the theta value at x and y. Let's think about when y equals to 0 here. So when x is 0, it's hard to guess what the theta is because I don't care. Although, so I only care about the point inside the upper plane. I need a value on the boundary just to know what's the value inside. At the point x equals to 0, there is a singular thing going on. It's not continuous anymore. So I don't care about the value at x equals to 0. But when x is less than 0, theta on this part of the point becomes pi. Because we define to be the inverse of cosine, and cosine value, inverse cosine value takes 0 to pi and measures the angle between the positive x-axis. So when I have point in here, the angle is pi. And when I have point here, when x is bigger than 0, it's 0. Right? I have certain value which is constant at one side and the other. Now I want to control this. I don't want the value changes at x equals to 0. What if I want to change it to a certain point when x is 1? Okay, so maybe I can just make it a specific point. Let's say I have 1 as my point where it changes the value. So for example, if it's C0 on the left-hand side and C1 on the right-hand side, how can I make a map? So let's think about hx0 equals to theta of x minus 1 comma 0. So when x is less than 1, then x minus 1 becomes negative 1, a negative number. So when it's negative, I know that theta always gives me theta, pi, as an angle. And when x is bigger than 1, it always gives me 0. So when x is bigger than 1, I want that to be C1, right? So, but when x is bigger than 1, I know that this theta is always 0. So no matter what constant I multiply with this here, doesn't matter. As long as I have a constant C2, C1 added here, then whenever I have x bigger than 1, I always get C1, right? So when I have x equals to x bigger than C1, what's the theta of this function? What's the theta? X minus 1 is always positive. So it's the same thing having a point translated by 1 or here, right here. So on the right-hand side of x is equals to 0, so you have 0 at the theta value here. So it always gets C1 because you have C1 added here. So if I want C0 when x is less than 1, C0, what should you do? Now, the value of theta becomes pi. So adding the pi times something with C1 and becomes C0, what you need is here like this pi divided by pi to make it 1, and then C0 minus C1. So then you get C0 and x is less than 1. So you have a composition of theta function with the translate function x minus 1 here. But translating doesn't change the harmonicity of function, because the harmonicity is about the differential. It doesn't matter whether you shift your function or not. So what if you want to have a random number that's 1 instead of 1? So instead of 1, I want to change my value of function depending on which side of my x is. So same thing, you just change this to x1. Okay? So here's another equation. So let's say I have 2 points and I want the value of function to be c0, c1, c2 on these three boundaries. Here, here, here. I want to have all different 3 values. And I'll still want the harmonic map. So I still have to use the theta function. So now it's complicated. I need to use 2 theta functions here. So I want to have a C2 on here. That's the biggest part. So we have x bigger than x2. So I need to have a theta function, something going on plus something going on, times theta of x minus x0, x1 here, and something times theta of x minus x2, 0 equals to c2, c1, c0, and x1, x2, and bigger than, less than x1. Okay, so let's look at this one first. I want c2 when x is bigger than c2, x2. So when x is bigger than x2, then this one becomes 0. This one also becomes 0. So I don't care about the coefficient applied here. What I want is simply the constant that I add here becomes C2. Then everything is fine. So how about when I have a point between x1 and x2? So then this one is still 0 because I'm in here. Whatever on the right-hand side of x1 becomes 0 because the angle is measured from C0 as an origin, so it's 0. But then this part is become pi, okay? So I want to have C1 after adding C2 with this something multiple of pi. So I need pi and C1 minus C2 right here to make it C1. Now, I want C0 when x is less than C1. In this case, now every theta is becoming pi. So still I have combining the C2 part and this part becomes C1. So what I want is here theta, not theta, C0 minus C1. So then I get the C0 when x is less than x1. So you can see how you can generalize this. So how many values, how many the boundaries you divide it into, you can just add more theta function with shifted so that you get all the values, boundary values you want in doing by doing this. Okay, so we have H and we have T. What's the next step? We just take the composition. So our H, which is a mapping between D to R, is given by composition of H and T. So again, D is mapped to H by T, and H is mapped to R by harmonic map H, right? We discussed here. Oh, by the way, so H here, so in the making of H1, Hx and Y, I only consider the boundary point, but if I define my H to be theta function, I could have Y not equals to 0 because I can have any function, any Y to compute the theta here. But as long as I have theta, I know that it's a harmonic because we proved there. So I have H, X, and Y to be, let's say, some linear combination of theta functions right there. So if I have the same boundary condition that I draw there, then it's C0, C1, theta x minus x1, y, so y comes here, and then pi C1 minus C2 theta x minus x2, y. Okay, so that's your h here. So t is already up there, so simply you take the composition to get h. Now the question is, how do you get the heat map? So this is a heat function. So heat function means that it's the temperature at every point x comma y. So you can get the contour line of temperature, meaning that the point on the line has the same temperature, but doesn't really give you the heat flow. It only gives you the heat contour, some sense. So in order to get the heat flow, is the line or curve that passes the contour lines of H perpendicularly. So as I think I mentioned before, so if this is your contour line of heat, so meaning that one contour line represents the line that has the same temperature, then your heat flow is something that flows in the perpendicular direction of each contour line that it passes. So how do we get that? You need something counterpart to the h, the small h. To obtain this, we need conjugate pair of h. So what is conjugate pair? So again, let's go back to the complex function. So meaning of complex function. So we defined our h to be theta here. Theta of z is the same angle that if I represent my complex number z as x comma y point. So we have z identified as x comma y, then this is r and this is theta. So if you consider the plane, two-dimensional plane, as a complex plane, your theta r is the same thing as the polar coordinate of the xy coordinate. So now once you have this r theta notation, then you can define so here I forgot the z here. You can define the function like this, which is log of r plus imaginary number I times theta, as a function that satisfies the following equation: ux equals to vy and uy equals to minus vy. So I'm assuming that this is my u and this is my v. Okay, so u and v you can consider as a two-variable function again. That is simply identified as x comma y. Right? Here, what is r? R of z is same as r of xy, so therefore it's the square root of x plus y squared. And what is theta z? We already computed this. So cosine of square root x squared plus y squared x here, right? So this is your u and v. So you have to take log here, but anyway, so this is your u and v. It satisfies these two equations. So what's good about having these two equations? It gives you a conformal map. So if a function x and y extending to u and v satisfies this equation, these two equations, then f is conformal. Conformal mapping. It preserves angle. Okay. So think about r and theta. So this is not a proof why. This is going to be give you idea why we are doing this. So since it's conformal, think about r theta. So think about the plane xy, and think about the line that is given by constant r and constant theta. So constant r means that it's the circle, right? So every time you have a constant r, all the points that has constant r is a circle with the center radius, center origin. And what is meaning of constant theta? Constant theta is a radial line that is from the origin here. So if you have these two lines, if you have this configuration of these two lines, they all intersect perpendicularly to get each other. Each point, each line you pick as a radial line, each line you pick as a circular line, intersect perpendicularly. So if you make a r and theta function like this, this u and v also has a same has the contour line perpendicularly intersect each other. So since r, the contour lines of r and theta intersect perpendicularly, so does log r and theta. So I'll explain briefly why it makes sense, why it happens, because what we are actually doing here with the function like this log of r and theta is that it's actually the log of z. So it's a analytic function, if I have to introduce this word. So it's a nice function in some sense. So it's a function that could be represented only in terms of z. Okay, so and also why we have such thing is that if you can represent your z as a r times e to the power of I theta, and that's a polar expression of r. And it could be weird to take a log of complex number, but you will learn if you take the engineering math 2 courses that the log property holds for the complex number. So you can split the log of r and the log of e to the I theta, and you can consider this I theta comes out from the log. It's the same property of log, real number log. So it's a log of r plus I theta log of e, which is 1. So this is what you get. That's your function. So your function, we actually defined our function just as a log of that function. And that preserves, and that is a conformal mapping, but also it preserves the angle here, angle between the contour lines here. So look at this one. So V is the heat map, basically the basic building block of our heat map. Okay, so we can do the same thing with the real part. So if our heat map is this one, that corresponds to this part of our construction here, the theta part, then what is the conjugate counterpart of that heat map? I'm going to write it as P. So this is going to be log of R, so log of, so R, so I need to take so actually I need, should I? Yeah, I should take it. So C0 minus C1 log of R of x minus x1 y and pi C1 minus C2 log of R x minus x1 2 y. So that's your phi, which is counterpart to the heat map, a heat function here. So if I draw the contour line of this V, then I get the line that passes through the contour line of heat function perpendicularly at every intersection point. But that's the counterpart function for the upper plane. I want the counterpart on the disk. So I need to take the composition of B and T in order to get the psi function, the capital psi here. So this now sends a point D to R, and that is also harmonic, which is conjugate, so it's a counterpart, counterpart to the H, the heat function here. So summarize H. So I cannot write the entire formula of H because it's now complicated, because it's a composition of complicated function T and small h here. Small h not complicated, that complicated, but T is complicated. So you have to use your computer program to compute the functions. And anyway, so this H xy is a heat function on D that gives the temperature at every point. And the contour line is it's the curve that has the same temperature. How do I have a word for that? So the lines that has equal temperature. The same temperature. And that is not a heat flow. That's not the trajectory heat flow. So it's the capital psi that is the, well, there's no name. It's the value of this psi doesn't have information. Well, maybe have information that you can infer in other studies. But right now, what we want from this function psi is the contour line that gives the trajectory. So the contour line gives the heat flow, which is perpendicular to the contour line of the heat function. Okay. The reason why it's heat flow is because exactly the same reason, because it passes the contour line of the heat function perpendicularly, because heat always flow in a fastest direction that changes the temperature fastest. The direction that changes the fastest, or value of function, any function, is it's the perpendicular direction to the contour line. Okay, so you cannot go sideways because the perpendicular direction is the fastest direction that changes the value of function, right? So if you deviate from that direction, then the extremal path is that you just follow the contour line, which doesn't change any value of function, right? So since it's perpendicular, therefore it's a heat flow, trajectory of the heat flow. Okay, so I've been fast explaining this, and I'll try to give the theoretical background. So not the detail. I mean, actually, the details are in the slide. So I advise you to read the detail on the slide. So in order to find out actual formula here, and also a lot more detail in here. So what we have to do is, well, quite not done yet. So we want to do something about the heat map on the disk. So the first task you should try, not not as a goal, final goal, but just the intermediate goal of your project should be, uh, first you set these four boundaries evenly distributed and at the north and south and east and west, and there are singular 4 points right there, and then try to get the heat map, the heat flow map, given the boundary values. So your boundary value has to be given first, then try to find out what the heat map look like. So you must find out which of these 4 points are mapped to which points on the upper plane. So for example, I'll show you the point here. So as I said, this is -1, and this is 1. This is minus I, and this is I. So these 4 points are mapped exactly at -1, 0, 1, and infinity. So you get 4 boundaries, 1, 2, 3, and 4, right? So you can imagine that if you have the map between this disk and upper plane, it's somehow you can get so this is opens up here, and then it somehow covers the entire upper plane here. So in the other way around, if you want to describe mapping from H to this, it closes up. So it's an infinite ray moving on two directions, but it closes up to meet at the infinity point. So there's infinity. There is no point, but so somehow you can imagine that the infinity points are shrinking down to this infinite ray, the end of this infinite ray at this point. So these are 4 points. So what you have to do is finding the small h that has a singular point at these 3 points with the 4 different C1, C2, C3, and C4 values on it. Now, that's the first task, and the next task would be it's up to you, up to your creativity. So, for example, what if you want to move your singular point? What if you want to change the range of your boundary? So, for example, not these 4 points, maybe you can change it to something like, so these boundary and these boundaries and these boundaries and these boundaries. They don't even have to be equally distant. So what if you have these 4 points as your singular point? Then you have to know how you could translate these 4 points onto the boundary point of the upper plane. So they're not going to be -1, 0, 1 here anymore. And also think about what you have to do is, let's say this is Z1, Z2, and Z3, and Z4 point. So assuming that it's a complex number, and say it's translated into 1, 2, 3, 4 right here. So let's see, x1, x2, x3, and x4. Let's say this is our corresponding points. Then how many boundary you actually have? So you actually end up having 5 boundaries instead of 4. So on the disk you have 4 boundaries, but when you translate these 4 points on the upper plane boundary, you have 5 boundaries, counting 1, 1, and 2, and 3, and 4, and 5, right? Right? You have 5 boundaries. But look at the 1 and 5 boundaries. Where does it correspond to in the disk? So you have Z4 right here. Z4 corresponds to X4, and Z1 corresponds to X1. So where does 1 and 5 boundary corresponds to? So it's between X1 and X5, right? In some sense. So in the disk, it's between Z1 and Z4. So as I said, the infinity closes up. Infinity is the point that corresponds to I. So all the rays that corresponds to boundary 1 and 5 on the upper plane closes up to the boundary between Z1 and Z4. So it corresponds to here. So precisely, so this one less than x1 is right here. This is 1. And one bigger than x4, which is part 5, is right here. So it's part 5. So what do we have to do? So if we have the same values on that boundary between Z1 and Z4, then we can just set the value, boundary value at let's see, C1 here and C5 the same. So if you set the boundary value of C1 and C5 the same, then it reflects on the boundary values between Z1 and Z4 in the unit disk. So nothing different. So there's nothing complicated here. So only thing you have to check is how does this boundary points on the disk translates into boundary points on the upper plane. So that's all. And also that's not maybe all, but you can try another one. So well, be creative. So instead of writing, I mean, you can make an animation of how it flows. So for example, like, you know, it seems like so so actually it's not a heat flow. So this is a heat map. Sorry. So it's just this is a heat. So it's a heat function. So it's a contour line of the same temperature, right? So this is a heat flow. This is heat flow. Okay. So it means that if I pick a point right here, so it will follow these paths to flow onto this boundary. So if I pick this point, it flows onto this boundary. And if I pick this point, it will just rotate in here, just keep moving inside here. So it somehow is showing you how the heat particle, if there's something like that, the heat particle moves around inside of the disk. So you might want to try maybe additionally to drawing the heat map. Maybe you pick interactive program that anyone who the user, if you pick the number, pick the point inside of the disk, then it shows the trajectory of that point inside the disk. That might be another way, another thing you can do. But this is just my idea. But be creative to do something about this. So that's basically the part project 5. So we have some time. Maybe I'll finish by 4. Before we finish, if there are any questions, let me know. Yes.
What would be like 6 and 7?
6.
Boundaries.
You want to make another boundary?
Yeah, 6
Yeah, you can make more boundaries then. Let me do it here. So 1, 2, 3, 4, 5, 6, 7. Well, same thing. So everything on the left is connected to the right part. So 1 and 7 here, right? 2, 3, 4, 5, 6. So all the rays on here will connect it to all the rays, the end of the rays on here. So let's say there's somewhere the y-axis, and if you translate to the disk, so let's say this is x1 and x6 here, and I'm assuming that x1 maps to z1 and x6 maps to z6 here. So, and there is a I, which corresponds to infinity, and these parts are mapped to here, and these parts are mapped to here. Oh, is it? Yes, yeah. So You might think it's weird to have a infinite region to close up in a finite region. It's not really weird because you probably have seen this picture. You have a sphere and the plane that touches the south pole. And if you have a north pole and another one point on the sphere, and you try to connect this line and then extend the line to the plane, let's say this is my point P on the sphere and P prime on the plane, then every point on the sphere can be mapped identically, one-to-one fashion to a plane, except for one point. The North Pole have no point corresponds to it. But however, you can think of this other way around. So you have a point on the plane and then try to map each point on the sphere. So in some sense, you're wrapping the sphere with your plane, right? So by infinite plane. So when you wrap, then you don't have a point that could cover the North Pole, but you can throw in one imaginary point called infinity to map to that North Pole. So that's what is actually happening. So when you close up this entire upper plane using the map, then you can close up except one point right here. But we can imagine that the infinity point, the point infinity, we can throw imaginary point that it is somewhere you can reach, that you go far and far away, and it corresponds to the point I. It's the same thing because if you go along the yellow boundary, you reach to I. It's same thing, same infinity here. And if you go to the left-hand side along the blue boundary, you also reach to I. So you can imagine that this I is imaginary point that represent the point that is far away from the zero. Okay. So any other questions? So it's perfectly normal that you don't understand some part or many part, because that's exactly why we are doing the project. So during the project, you have to figure out what you don't know, what you should understand, and so on. So uh, understanding is not the it's not the reason. It's not the factor that you should consider when you choose your project. So just so the reason why I'm talking about this is next lecture, the next week, Wednesday, we're gonna pick the second project. So we're gonna pick from the fifth project to the ninth project. Among these five projects, you should pick one for your second project. And well, I should say technically all the projects are as hard as are equivalent. They're equivalently hard, or maybe you could say easy, but the level of complication in the technical part, like programming, it's equivalent each other. But the theory behind it also equivalently hard. So there are all this there are hard, at least hard as this one. So maybe this one getting a little bit harder if you want to go deeper than what is required. But anyway, so if you are just interested in that the output, if you can create output that is interesting, and you have a creative idea to produce an interesting output, then don't hesitate just because of you didn't understand some material that I gave you. Because even if you choose another subject, then it might be as hard as this one. So if you have any question, let me know. We're gonna talk about the project 6 next time, and also we're gonna pick one. So before you come to the class, so keep in mind which project you want to be in, and also I'm not sure why people didn't come that much today, but I hope everyone come next Wednesday because we're gonna choose the topic. That means we're gonna form a group. So if you want have a certain member in your group, for the second project that you have to, then you have to circle your names together so that I can make you in a same group. Otherwise, I'm gonna randomize the group here. Yeah, make sure that your team member, if you want to be in team, the second team, to participate, to come to the class. Um, it's not allowed to have write the other member's name, so only write your name on the sheets that I'm going to pass around. Okay, so see you on Wednesday.